Last topic of the day, and thanks for coming. This is about Akka and Kubernetes, the beginning of a beautiful relationship. So I know I've given this talk in other conferences, so often I ask, do you know what Kubernetes is? But I don't have to ask that question here, right? You guys, after 2-3 days of this, you guys know a lot more than I do about Kubernetes. But how many of you have heard of or of Akka before? Oh, wow. Okay. How many are using it? Okay. So yeah, this is a talk about Akka running on Kubernetes, but I wanted to try something real quick. I usually don't do this, but today's a little unusual. It's been hot. So I thought maybe we could start out with a little refreshing moment. I've been thinking about jumping in a pool all day long, and it's been so hot. It's like, okay, so I found this video, and I thought it was kind of a fun way to start. But enough of that. So my name is Hugh McKee. I'm a developer advocate at a company called Lightbend. You may not have heard of us or not, but we're the company behind Scala. So I don't know if you guys have heard of Scala. Scala is an object functional programming language. One of our co-founders of Lightbend is Martin Ordersky, the creator of Scala. And the other co-founder is Jonas Benair, who is the creator of Akka. So a couple of really interesting, heavy, technical heavyweights that started our company, and I'm delighted to be able to work there. We also have an open source framework called Play, which is a reactive, asynchronous framework for web services. And it's been reactive before reactive was cool. Reactive has gotten cool in the last few years, but we've been talking about asynchronous for the last 10 years. By the way, Akka and Scala both are celebrating their 10-year anniversary this year. And then the new kid on the block is an open source framework called Lagom, which is a microservice framework that's built on top of Play and Akka. And it's available for Java developers or Scala developers. And so is Play and Akka. If you're a Java developer, you can use Akka, you can use Play, you can use Lagom, and of course, if you're a Scala developer, you can use them. But I'm a developer advocate, and I focus on the Java community. But in any case, Lagom is a microservice framework for people that are new to microservices. So it's kind of a building microservices with guide rails. But I'm not here to talk about that. I'm really here to talk about why Akka loves Kubernetes. So before I get into this, just quickly, I took this paragraph from Wikipedia. This describes, I think, very succinctly what the actor model is. It's the very first paragraph, and whoever wrote it, I think, was just brilliant. But normally I spend more time in this, but just for the sake of time, because it's a little bit shorter talk, the way I try and explain actors in the actor model, and the actor model, by the way, was invented back in the 70s, so it's been around for a while, and it's been in use for a while. And in Akka, it's been, like I said, 10 years. But in any case, imagine a world where everybody only communicates via texting, which is kind of the world we're going into these days. Everybody's walking around and all they're doing is texting. All we're doing is texting each other. I ride on lots of airplanes and I see people through the whole flight. They're just texting each other. I don't know what the hell they're talking about, but they're texting all the time. Well, this is the world of actors. The way actors talk to each other is very much like humans talk to each other texting. Because with texting, when you send me a message, you're sending me an asynchronous message. You're not waiting for me to respond. Now, you might be, emotionally waiting for it, but you're not frozen in suspended animation waiting for me to respond. And the only way you can communicate with me, you can't touch me, you can't talk to me, I can't see you, nothing. The only way we talk, the only way this world goes, and which is the way our world seems to be going, is that actors talk to each other, sending each other asynchronous messages. Now, the cool thing is that when you write an actor, it's just regular software. If you're a Java developer, it's just a Java class. If you're a Scala developer, it's just a Scala class. The big difference is, though, is that none of the methods or none of the code in your actor is directly accessible outside the actor. So there's a kind of indirect way, just like text messaging, that messages get sent into actors. And that's the fundamental building block of actor model systems. which have, again, it's over 40 years old. It's been used to build some really big, heavy-duty, non-stop, high-performance types of systems for decades. And it's very, very powerful. So, I like using the texting analogy because it kind of puts things in perspective. Like when we're working, when I'm working on an actor system, it's really fun. And it's usually better to do it with somebody else besides yourself, because it's like playing chess with yourself. I send a message and then I'll play the other role. Did I get that message? Going back and forth. But it's easier to kind of go, I send you a message, you're an actor, I'm an actor, we're exchanging messages. How does the system work? We walk through it that way. But another analogy is that actors have this real simple characteristic, and they're kind of a very simple building block, a software building block, which is somewhat like a Lego block. Lego blocks have very simple principles, but people do really, really elegant things with them. So and I grabbed this picture off the internet. This is a Lego castle. Taking those fundamental building blocks. You should see some of the systems that people build with the actor model. When I first got into it, it blew me away, and I've been writing software for a very, very long time. So Kubernetes, as you guys know, is a container management system. But I look at it from the perspective of, I'm a Java developer, I'm writing Java code, I want to run my freaking code somewhere, and don't bore me with this too many details. And this is why I love something like Kubernetes, because basically I can look at it, it's like, all right, I've got this JVM, this Java virtual machine that I want to run and make it easy for me. And Kubernetes is one of the best things I've seen in a long time to make it easy, because before that, it's like you write your code, then you got to go this, and you do that. You got to get a machine, you got to get access to the machine, you got to deploy it to the machine, you got to do Ansible, you got to do all these different things just to get your program running. The thing I like about Kubernetes is that it's making it easier. And it's giving me this bonus environment where it's resilient and elastic, which I'll be bringing up some more later on, which is things like, okay, my code's running, but not only is my code running, but if it takes a hit in traffic, it can, it can grow. It can increase the capacity to be able to take more traffic. And Kubernetes is doing that for me. And if it takes a hit where something breaks, Kubernetes goes, oh, this application wanted 5 pods running, 5 processes running. We're down by 2 because some hardware broke somewhere. It's going to bring me back, my application back up to 5. I don't care how it did it, because all I want is to run my code. Let the Kubernetes environment take care of it for me. So I want to show you what I got running on my laptop is Minishift, and which is OpenShift on the laptop. And I like using OpenShift because it's a nice wrapper around Kubernetes. There's many different ways you can do it. So I got this Minishift environment running on my laptop, and I got some pods running. So I got 3 pods running already on my laptop. But what I want to show you, though, is, all right, let me get back there. I'm going to bring up a console. So this is, the OpenShift console, and I've got some projects set up in this, and the one I want to show you is this one I call Akka Cluster Demo. And I want to start with, I'm by no means a Kubernetes guy, but I know enough to be dangerous where I can get my code running. That's really what I care about. But I was able to set up a load balancer, configure a load balancer, and I've got an endpoint to a little demo app that I've got running here. So this is a visualization of a live system running. Those 3 pods that I showed you at the command line quickly a moment ago, this is a visualization of those 3 big circles here. These represent kind of the pods, and the tree coming off those circles represents stuff running in those pods, which are actors. And I'll explain more as we go along. But you can see it's moving around. So there's things happening at the Akka level in this system. is kind of simulating activity in this demo system. And it's a running live system. So let me explain to you a little bit about what all these little circles are and everything. So somebody nicknamed this the crop circle at my company, and I kind of liked it. But what I'm trying to show here is visually show a lot of stuff. So first off, like I said, each of the three big circles are kind of the stuff running inside of a Kubernetes pod, which is running a Docker container, which is running a JVM inside that Docker container. And then all the stuff, the tree coming off that big circle are actors that are running inside that JVM. Okay? The circles themselves, though, and these are Akka actors. And if I get time, I'll show you some of the source code. And there's a project that you can grab from GitHub with this demo, including the visualization. So the most important ones are the little blue circles on the perimeter. The little blue circles are called entity actors. And it's an entity, meaning it's a thing, it's an object. It's like you can think of it, say, as an order or a bank account or an IoT device, depending on the application, but it represents the state of a physical thing, like the state of an IoT device or your current balance or your current order status, something along those lines. So this is where business logic runs. You're adding items to the cart, you're removing items to the cart, you're changing the balance of your bank account, whatever the entity might be. Here I'm just simulating this is where entities run, and they're running on the perimeter. So those are the things that were coming and going. You could see things appearing and disappearing as the simulation was running. And this is, again, it's a simulation, but it's a live Kubernetes environment running a live Akka application on my laptop is what we're seeing in the visualization. Now the green circles are actors as well, but these actors are called shards, and their only role is to distribute a work around the cluster. And this is important because the state of the cluster can change. At one moment, maybe we only have one pod running, which means we only have one Docker container, which only has one JVM running. But maybe we want to scale the app up, and maybe we want to scale it up to 3 or 5 or 50 or however many this application needs. Those shards are used to distribute the work of distribute entities across the cluster, and I'll show you that in action. And then again, the big circles represent kind of the things running in a pod. They also represent individual actors that run one per JVM, but I won't get into too much of the detail of those here. And then these little pinkish circles, what I'm trying to show there is this is when an entity shuts itself down. So what's happening is that, imagine that this is really representing a microservice, a single microservice, running in a cluster, but pretty much as a single system. And there's one actor per order. So it's like, if I'm building an order from my phone app, I'm talking to one of these actors. If you guys are building phone orders for your orders, you have different actors. Each of us has our own actor that's handling our particular order. That's what this is for. So what happens is that when messages are being sent to these actors, they're alive. They stay alive. They maintain state. They know what the order looks like. They know what the state of IoT device is, whatever happens to be the system, what it's doing. But when it stops receiving commands, they shut themselves down. It's a simple mechanism, but the actor just stops. It's I'm not doing anything, so I might as well get out of the way. So that's what's happening. What you're seeing when they kind of poof out of existence is that actor stopped receiving commands and just went away. But again, this is just kind of peeking into a way to build a single microservice as a cluster in Kubernetes. And I'm just trying to show here that this is a system, one microservice in a system of microservices. I'm not saying that every single microservice has to be written this way, although I'd love it, but it's just that this particular microservice that we're looking at is implemented in this way. So let's go back to the crop circle. So, we got 3 things running, and I want to go back to the console for a minute and show you in the console where it's showing that we have got 3 pods running. So here's 3 pods that are running. But what I'm going to do is I can simulate a failure. So, and I've just set it up. If I click one of these big circles, I just set it up in this little demo app where it's going to shut down the whole JVM, which is going to shut down the pod. So when I do that, what's going to happen is that pod's going to go away eventually. There it goes. And then remember the green circles, there's 15. What we're going to see very quickly is those 15 shards have redistributed themselves across the remaining 2 nodes in the cluster. Okay? So, and then now we see a pod come back. So this is kind of the relationship between Akka and Kubernetes. Akka saw we lost a JVM and immediately reacted to it and redistributed the load. Kubernetes saw we lost a pod and it immediately reacts to it and go, hey, this thing's currently set up to be running 3 pods. I need to start that. I lost a pod, I need to start a new one. So a new pod was started up. Akka now sees that pod rejoin the cluster, and the actors react to that, and they start migrating work back over to that pod. So that's kind of an example, as I mentioned earlier, the resilience, where it's the combination of the kinds of things that happen inside of Akka in orchestration with the things that we get with Kubernetes. That this is like the perfect platform for Akka. This is something we've been waiting for since like 2013. Now, the other thing is that say this microservice gets a hit in traffic and it needs to scale up. Well, that's something that is a nice feature of Kubernetes. So I'm going to scale this up to 5. And so it's going to take a bit. Kubernetes gets the command to do that. It starts spinning up some pods. And what we should see here is that the pods will spin up. They bring up new Docker containers. The JVMs start up. Now, when the JVMs start up, they need to, the Akka code in this example starts up, and it needs to rejoin the cluster. So there's this process going on where it's rejoining the cluster to come back in, and you can see one of the pods coming in here now. So we got a 4th one coming in, and you can see a shard has already moved over there. So we're starting to rebalance the work. In a moment, we should see the 5th one come in, and there it goes. The 5th one's come in, and it's the same thing. The green shards are reacting to that. We got more capacity. Let's redistribute the load across the cluster. Now, the cool thing about this is developers using Akka, a lot of this functionality is out of the box. What I'm showing here is out of the box. Now, the entity actor is something that I wrote, that you would write as a developer. And the code that sends messages, like when HTTP requests are coming into this microservice, for a particular cart, somebody's got to take that message and then, coming in as an HTTP request and create a message to send off to the actor. But the routing of the message to the actor is also handled by some of the out-of-the-box capabilities that are provided in Akka. So we really, as developers, we're just focusing on writing the entity actor, which is, again, where the business logic is at. So, we've scaled up here, and we're running on these 5 pods now. Boy, this mic won't stay on my ear. And, so say the spike is over, so I'm going to just bring it back down. So we're going to scale back to 3, and pretty quickly, those 2 go away, and pretty quickly, the shards redistribute themselves back across the remaining parts of the cluster. So, there's not magic here. Stuff was running in those JVMs stopped. The stuff that was running there stopped. So those things had to be restarted somewhere else in the cluster. Okay, so it's not magic like it's magically being moved, but it's there. The plumbing is there to make all this work. So this is really the components of a reactive system. The term reactive has gotten really, really popular in the last few years, and almost always it's talking about reactive programming, which is great, because we've been talking about reactive programming for a long time. Asynchronous programming, things like that, that's really good stuff. But we've also, at Lightbend, we've been talking about reactive systems for a long time. And this is what attracted me to stuff like Akka. I used to work at HP, and I got to the point, I was in IT, I was an architect, a developer, and I was also one of the folks that got called at 3 o'clock on a Saturday or Sunday morning when we had a production outage. And it happened over and over and over again. I'm sitting there going, I don't like doing these things. I like sleep. I like spending some time with my family. I want to build systems that don't break. And when I came across Akka, it was like, okay, I'm starting to see something that gives me a capability to build systems that are built from the beginning to take things like, yeah, you lost a node, so what? Oh, you got more nodes. Okay, cool. It wasn't a big deal. This was just second nature in the way the systems worked. So so Akka had that ability to run in a cluster, but it didn't have that orchestration layer, the thing that Kubernetes gives us, until Kubernetes came along. So let me just show you a little bit of the project. So this is just a Java Maven project. The only thing that I've added to this project, and I think you've already seen plenty of examples of this, is some YAML files that describe the deployment of this application and some role bindings, and then I had to create a load balancer. But other than that, this is, if you've done Maven before, this is just a standard POM file, which is a file used for building the project. The only thing I had to add to this POM was a plugin to create a big jar. And a big jar meaning a jar that contains all of its dependencies. So it's a self-contained jar that could be just run, like within a container and doesn't need anything outside of the container. So this plugin, this Maven Shade plugin, builds that for me. And then the other one that's really nice, because I don't like dealing with Docker files myself, but that's a personal thing, is there's a Docker Maven plugin. And this is the thing that builds my Docker image. So when I do a Maven build, it builds me a big fat jar, puts the jar into a Docker image, throws it into a repo, local repo, and I've got that part of it done. The code itself, let me just show you a little bit of where things start up. This is the class where this Java project starts up. It's just got a main method that invokes one of the first things and this is stuff I wrote. I'm just a Java developer using Akka. Nothing, this is right out of the documentation. Nothing exotic here. So one of the first things you have to do is create an Akka system, which is just this one line of code. Now, there's a configuration file that describes some things, the characteristics of this Akka system, but it's fairly straightforward. Then I call this method that I wrote that's called bootstrap the cluster, which is down here in these two lines. So this is the code that I needed to use. So when this thing ran, when a Docker image ran, like when I scaled up and 2 new Docker images came up and 2 new JVMs started, it ran this main method in this class. This main method invoked these 2 lines of code. These 2 lines of code triggered Akka code to reach out to Kubernetes and say, hey, am I in an existing group of pods? Are there other pods like me around or not? And if there is, Kubernetes gave this code back a list. And then this JVM used that to reach out to the other pods over the network because it got the network addresses back to say, yeah, there's 3 other pods running, like in the example I ran when we went from 3 to 5. So to say the 4th node started up, it executed this code, asked Kubernetes what pods are out there, here they are, got the network addresses, and it started communicating with them, say, hey, I'm here, I would like to join the cluster. So this is where Akka runs in a cluster where the nodes in the cluster, and this is all managed by the Akka code, start talking to each other and forming a cluster. So there's a whole life cycle involved and everything. I won't bore you with all the details. But this was the code I had to write to make this all happen. And then just for fun, just show you a little example. Here's an example of creating an actor. And this one line of code I'm highlighting here, that the actor system, I'm saying, hey, actor system, create an actor of this. And props is, I don't know, it's my way of explaining it is it's kind of like a wrapper around the constructor of this class. But it's a wrapper that's needed to create an instance of this class and then make it an actor. And Akka does the magic to make it happen. So I'm going to have to move on because we're running out of time. So just quickly, what's happening here is that, you know, those blue circles at the perimeter, this is my attempt to try and explain what's happening. I'll say it's you and me and some other person. We're sitting on our apps, and we're sending in, you know, requests to this microservice, which is running in this cluster. In this example, there's 4 pods running. There's 4 JVMs running in a cluster. And we're each sending in our requests over the network. Those requests go through the load balancer and land on some random node in this cluster. Now, Akka gets those requests because the thing that took the HTTP request, built an object to send a message to an actor, and then Akka took care of the routing of that message across, you know, from where the HTTP request came in to where the entity actor is. So in the example I'm trying to show here, you are talking to entity 64. Entity 64 happens to be like, you know, the ID of your order or your, you know, whatever. And following the blue line, your HTTP request landed on this top left JVM. That top left JVM got that HTTP request, created a message, which is just a Java object, and then it sent a message to a local actor, which is a local actor that was created at part of the startup here, which is responsible for routing the message to wherever the entity actor happens to be. Now, in the example, the entity actor happened to be on another node in the cluster. Okay, so the message gets serialized, sent over the wire, deserialized, and then forwarded on to the actor. Now, again, I didn't write this code. You don't write this code. There's other actors that come with Akka out of the box to do it. Now, if we wanted to write something like this, we could do it. And if I had more time, I could show you some of those things. But this is not rocket science when you're using something like Akka. So this routing of messages across the network is something that Akka is built to do. As an example, you know, Akka is built to scale to something like millions of actors per JVM, millions of messages per second. One of the classic examples of a customer that's using Akka at a very large scale is, well, I believe it's PayPal. They're doing like 1 billion messages a day on, I think it's an 8-node, 2 CPU VMs. And they're doing 1 billion messages a day. God knows how many messages, actor messages, that's generating. But that's, you know, millions of actors running, you know, in relatively small footprint. And it has the ability to adapt. If the cluster changes, say in this example from 4 down to 3, hopefully all the customers, the idea is that none of the customers even see that happened. We lost a machine. That could have been, you know, could be catastrophic in some situations. The system's supposed to be able to go, oh, okay, we lost a machine, who cares? We just redistribute the work. Let me just take a real quick dive into the entity actor. This is just a Java class. This is, you know, so it's Java. I just called it entity actor. I'm extending an Akka base class. But the main thing I wanted to show you here is I have to override one method, which is defining how this actor handles incoming messages. Now, this is called untyped, Akka untyped. There's a new thing, relatively new, that's called Akka typed, which is a more strongly typed way of handling messages. But in any case, this is the old way. But all I'm doing here is I'm saying if messages are coming into this actor, this method is given those messages. The method here looks at each incoming message and it says, oh, if it matches that it's a class of this object called command, this class called command, then invoke this command method. If it's a query object, these are objects I just created as a developer, then invoke this query method. The command method's down here. There's nothing special to it. The main thing I wanted to show you is that this is just a simulation. So typically in a real application, we'd be doing some persistence here. But that's a whole nother story that we don't have time to go into. But the thing I wanted to show you here is that this is where I'm sending an acknowledgement back to whoever sent me this message saying, all right, yep, I got your message. So it's like you texted me a message, I got it, I did some work, and I text you a message back saying, I acknowledge, I got what you asked me to do, and here's the result. But this is just not, it's not a requirement of Akka, it's just the way I implemented this actor, that my actor receives a message and it sends a message back to the sender. So the idea is that, and this is the beauty of the Akka running on something like Kubernetes, is that here we're down to one pod running in Kubernetes, which means we got one JVM. And the system's running along just fine. And we scale up to 3 pods or more, whatever, number of pods. And now the system, this microservice has more capacity. If we lose a pod, who cares? We know how to deal with that. That's, there's this concept of let it fail. When you're building a system, I like calling it throwing rocks at the design. And I always say, remove the word if from your vocabulary when you're doing, like system design. It's when. When this breaks, what are we going to do? When this fails, what are we going to do? When the network slows down, what are we going to do? Face it head on. And the idea is that those shards, in this particular example that I'm showing you, if we lose a machine where, say, 3 of these shards we're running on, the system knows how to react to it. This is simple, pretty simple actor mechanics that's dealing with this. One final thing I want to show you, because I've really run out of time, is this tree. So what this app is doing is, it's just anybody heard of D3.js? It's a JavaScript framework. It's really cool. I know enough JavaScript just to be a little dangerous, so I grabbed an example template, which is millions of examples, and I use that to do this visualization. But the tricky part of this is that entities are popping up all over the cluster, but I don't know where the web client, my web browser, is going to come in and ask for this. This is a whole tree. So what has to happen is when an entity actor starts up, it needs to send a message to another actor, which is a simple actor-to-actor message. And then when that actor gets it, it forwards that message to its counterparts across the cluster. So what's happening is the tree is being built across the cluster. So no matter where my client comes in, they're seeing a pretty much consistent view of the tree. And I did this first because I wanted to do this visualization, but it's also kind of an interesting example of how actors can communicate with each other, as well as not only just directly sending messages to each other, but also sending messages to counterparts across the cluster. Very, very powerful stuff. I mean, well, it's hard to even imagine trying to do something like this, writing code, going over the network, deserializing, serializing, all that crap that you have to do. This is a few lines of code. If you want to see it, I can show you after the talk. But it's like 10 lines of code to make this all happen. There's this concept of singletons. I don't want to go into that right now. But this was cluster sharding, what I was showing you. It's called Akka Cluster Sharding. It's heavily documented. It's a heavily used pattern. It's been around for a while, and it's very powerful. And it kind of builds towards, if you you may not have heard of this, or if you have, but it's called event sourcing, command query responsibility segregation. So an event-driven system, this is beautiful for events, an event-driven system. And it fits, where each entity actor is the thing that's receiving commands, creating events, persisting them, and then maintaining state. So if you're familiar with event-driven systems and event sourcing and CQRS, we deliberately built this pattern of actors to support that. So that's kind of it. That, like I say, we were waiting for something like this for a while, and finally some lovely day came along and we realized Kubernetes was out there, and I remember when I first saw it and I thought, oh my God, this is the perfect platform. I wish I had this when I was back at HP, because we had to kind of build our own orchestration layer. The source code to this project is available on my GitHub, and I'll publish these slides. But you can just download this and play with it. Run, download and install, say, Kubernetes on your laptop or Kubernetes in your favorite cloud, wherever, OpenShift, Google Cloud Platform. I also have a series of other projects that are kind of build up to this project. They're all Akka, Java, Maven projects. And I wrote a little booklet on if you're interested in the actor model and you want to read something about the actor model without getting into the code, but it's more into the theory, kind of a quick read. This is a free download. And I'm done. Thank you. I don't know if we have any time for questions, and I'll be around. This is the last talk, right? So, yes, sir.
Hi. So, in your model where you had the Akka cluster, node clustering, where is the orchestration taking place between all of those JVMs being able to communicate with each other and then know, okay, now I'm assigned to this pod or I'm assigned to this pod? I'm sorry, I'm using the wrong terminology. Correct me.
No, I get. So the question is basically, you got all these JVMs running in pods. How do they talk to each other, right?
It seemed like when you were forwarding messages so that you would get the same tree every time you hit the load balancer, you kind of designed almost accidental consensus because everything was sending messages to every other pod.
Not every incoming message, but what's happening before that, though, is that, say, when a new pod starts up and the JVM in that pod starts running, that JVM reaches out to Kubernetes and says, are there other pods like me out there? And Kubernetes comes back with a list. So it's either like it's the first one or there are other ones out there. And basically what Kubernetes is giving back to the JVM is the network addresses of all those other pods. And then part of the bootstrap process is that this is at the Akka level. Akka is then starting to talk to the other JVMs saying, hey, I'm here, I want to join a cluster, which is a whole formal thing in Akka.
Okay.
And then once the messaging starts coming in, that's very direct.
Okay.
So a load balancer could randomly drop a message, an HTTP request to any one of them.
But is there like a concept of leader election? Like how does that process get distributed?
It's called a masterless system, Akka. There's no master. The leader there's a leader there, but it's only there to say, all right, everybody agrees that you're a new member of the cluster, so we're going to promote you from a wannabe to you're up.
Okay.
Okay? So the leader, there's one place where that decision is made, but that's the only thing the leader pretty much does.
Okay, thank you.
Other than that, it's a leaderless, masterless system. Okay, time to jump in the pool.